tell us about the Pinnacle architecture?
Thanks, Stephen. So as Stephen said, I'm going to talk about the Pinnacle architecture. This work is not quite on the archive yet. It'll be in the archive in the very near future. So technically, this is an exclusive preview. So we just ask that you don't share videos and photos and things online publicly until it's out on the archive, but that will be very soon. So the bulk of this work is going to be about how we can build a new fault-tolerant architecture, the Pinnacle architecture, and how we can use it to reduce the cost of breaking RSA 2048 encryption to 100,000 physical qubits using quantum LDPC codes. This is joint work with my colleagues at Iceberg, Lucas Brent, Omka Chandra, Evan Hockings, Nuatan Busbin, Felix Thompson, Sam Smith, and Larry Cohen. So I want to start by going through the essentials of the talk in one slide. If you were out late last night and can only stay awake for 5 minutes, make it this 5 minutes. So the Pinnacle architecture, what is it? It's a fault-tolerant quantum computing architecture. So what we mean by that is it's really a way to construct a working quantum computer out of the kinds of components of fault-tolerant quantum computing. So we're going to take in things like code blocks and ancillary gadget systems and magic state facilities, all these sorts of things. The Pinnacle architecture is going to be how we assemble them into an actual architecture that we could then imagine putting into hardware and really running in order to run universal quantum computation and do actual applications. So the Pinnacle architecture in particular, the key to it is that it uses quantum low-density parity check codes. And in particular, the main goal of that is to reduce the space-time overhead of this computation compared with alternative architectures. So in particular, low-density parity check codes, I think we've heard a lot about them at the conference already, but the most important thing to know about them is that they can have a higher encoding rate than more conventional codes like the surface code, in that they can encode many logical qubits in a single code block of comparable size to the surface code. And that means that we can achieve a lower space overhead, that is fewer physical qubits per logical qubit, using the low-density parity check codes than we could using a surface code architecture. But importantly, we're also going to focus on maintaining a low time overhead while getting these space overhead savings. So in particular, there was recent work last year from IBM with their Torta-Gross architecture, where they achieved these low space overhead results using LDPC codes, but at some trade-off in terms of additional time. We're going to avoid having that trade-off, so we get a true space-time overhead reduction. And I'll talk as I go forward about how exactly we can do that. Importantly as well, because we're using low-density parity check codes instead of surface codes, we do need longer range connectivity than is necessary with surface code architectures. So surface codes can depend on only nearest neighbor interactions. We're getting the higher encoding rate by allowing longer distance interactions. But importantly, we're not going to require all-to-all connectivity on the scale of a whole 100,000 physical qubit device. And we're not going to require connectivity that scales as the number of logical qubits scales up. So essentially, we're going to have modules of this code being code blocks that we'll then equip with measurement gadgets to make them processing blocks. And all of the connectivity we're going to need is going to be constrained to the scale of one of these blocks or nearest neighbor blocks, which means that we have a constant range, a constant extent of connectivity needed as we scale up the number of logical qubits. And this architecture also has nice properties in terms of being modular and parallelizable. So I've shown a couple of examples of what different instantiations of the architecture can look like here. You can see that it's made up of these individual blocks, like processing units and magic engines and memory that I'm going to talk about. These things constitute modules, and the idea is that we assemble the architecture from these modules, and we can sub in and out different choices of objects, like which LDPC codes we use, what kind of magic state facilities we use, into this architecture to get different results. And we can also achieve parallelism, as is kind of shown in this second example, by using lots and lots of copies of these processing units in parallel without needing to scale a whole big object up. So we have this nice modular structure, which is also then going to have nice links to the kinds of modularity that is increasingly becoming clear is necessary for hardware, where we don't want one big monolithic structure, we really want different modules that can be wired up with more limited networking between them. So it's great to have this theoretical architecture, but what we really want to show is that this is an architecture that actually delivers on what it promises. So we want to show that if you really do a detailed compilation of an important benchmark application to this architecture, that you actually get the kinds of results you should theoretically expect in terms of the low overhead. So we've chosen to benchmark to the problem of factoring to a variant of Shor's algorithm. The main reason for this is not necessarily because we're most excited about breaking RSA 2048 encryption, but we think this is the clearest cut benchmark application to compare to. This is a problem that, unlike a lot of quantum chemistry problems and material science problems might be interested in, it's been a kind of publicly available problem for decades. There's a particular 2048-bit integer you can go online and get and try and factor yourself. So there's been plenty of scope for classical computing workers to try and solve it, and no one has. And it's a kind of clear-cut problem. You factor this number or you don't. So we wanted to have that kind of clear-cut benchmark, which we think then gives the fairest comparison to what you can achieve on other architectures. In particular, what we find then is compared to the previous best result due to Craig Gidney from Google last year of how to factor 2048-bit RSA integers with close to 1 million physical qubits, we're able to do this factoring with less than 100,000 physical qubits, so achieve an order of magnitude reduction. In terms of runtimes then, we can achieve the 100,000 physical qubit result with a runtime on the order of a little less than a month, but we can easily scale up make small increases in the physical qubit number, for example, to 150,000, in order to get better runtimes of the order of a week. So even in that time scale, we're still retaining this lower overhead for that runtime. I'll talk more about this as I get towards the end, but we also consider a range of different parameters that might be relevant to different hardware platforms, so in particular different code cycle times. So the code cycle time is the time required for one round of error correction or one round of syndrome extraction. So this varies a lot from hardware platform to hardware platform. Hardware platforms like superconducting qubits that obviously Gidney at Google is interested in are expected to have these fast code cycle times on the order of a microsecond, whereas other hardware platforms like trapped ions or neutral atoms are expected to have a code cycle time more like a millisecond. So we considered these range of parameters, and we think that's important as well to show how this architecture is relevant to a range of different hardware platforms. So as I said, that's the key takeaways of the slide, but hopefully you won't all fall asleep. Let's get into the actual meat of it now. So I want to talk first about what's the motivation, what are we trying to do here, both in this talk and generally in the work that we do at Iceberg Quantum. And the key point is that theoretically it's long been expected that using LDPC codes should allow you to reduce the overhead by an order of magnitude, simply because of the higher encoding rate. But given that theory, it's sort of strange that the best result currently for this benchmark problem of RSA 2048 is this one from Gidney using a surface code architecture. So the question remains, why is it that we haven't been able to beat this result by the order of magnitude that theoretically should be possible? Why are people still using surface codes for even the theoretical best results they can get? And I think the short reason is there's a big difference between what's involved in a quantum error correcting code, the kind of thing we've talked about here that you might study abstractly using chain complexes and things like that, and a full fault-tolerant architecture that you could actually plausibly intend to be implemented in hardware. And what we really want to do is, with the Pinnacle Architecture, show that we can take the gains that you get in overhead with LDPC codes and actually retain them even when we apply them in a real application. That's really the core application, and in terms of what we want to do with this then, we want to take this to actual hardware companies, people interested in building real quantum devices, and really see that this is something that can be put into practice and really accelerate the time frame in which we expect to see these kinds of applications. So if I get into the background now, there's one key piece of background that I want to start with because it will motivate why we build the architecture the way we do and how the architecture is going to meet the requirements of a universal fault-tolerant quantum computing architecture. And that's to start with how we do the compilation on this architecture. So the basic type of compilation we're using is what's called parity-based computation. And essentially, that's a way that we're able to do arbitrary quantum circuits using only Pauli product measurements supported by ancillary T-states or magic states that we can inject in. So by Pauli product measurements, what I mean is Pauli measurements, but Pauli measurements that can be across any set of logical qubits. So in general, multi-qubit logical Pauli measurements. So how does this compilation work? How do we go from a more standard Clifford plus T circuit, that is just a circuit written in terms of Clifford gates and T gates, to this Pauli-based computation framework? Well, we can think of it as a three-step process. We start in the same way that I think just about any standard fault-tolerant compilation would start, by replacing the T gates with T-state injection. So we have a circuit then where we can take this ancillary magic state that we prepared offline and inject it in using these Pauli product measurements, like the ZZ measurement there, along with Clifford operators. We then have a circuit that consists only of Clifford operators and Pauli product measurements. So we can deal with the Clifford operators by commuting them through the Pauli product measurements. The result of that is that when we push a Clifford through a Pauli product measurement, the measurement remains a Pauli product measurement, but the basis is now conjugated by the action of the Clifford that was pushed through. Because Cliffords map Paulis to Paulis under conjugation, though it remains a Pauli product measurement. And then when we get to the end of the circuit, we can assume that all of the logical qubits will be measured in some Pauli basis at the end. So we'll absorb in the Clifford at the end. And again, that will change it to a different Pauli product basis. but we'll end with a circuit that just has these Pauli product measurements along with these two states that we need to inject in. So if we look at what we can do with that, if we have an arbitrary Clifford plus T circuit that has k logical qubits, tau T gates, O other intermediate measurements that may be present in the circuit, and can have any number of Clifford gates, then we can implement that using tau plus O plus k Pauli product measurements supported by tau T states. So the way we're going to design our architecture is such that each of these Pauli product measurements can be done in one logical cycle of the architecture, that is approximately d rounds of syndrome extraction, so that we can then implement a circuit in essentially this capital T logical cycles. So I want to get into the core modules of the architecture now. So the key modules are these processing units, and these are the objects that allow us to do these Pauli product measurements. So what is a processing unit? Well, a processing unit consists of a set of processing blocks that are bridged together. The idea is that each of these processing blocks allows us to do arbitrary Pauli product measurements, and this bridging operation is a way to allow us to do Pauli product measurements across multiple blocks. What are the processing blocks? Well, the processing blocks themselves are LDPC code blocks. So think of taking an NKD LDPC code and actually putting it on some set of qubits, or actually instantiating it in a real set of qubits, and then equipping it with this gadget system, an ancillary system for generalized surgery. So I think we've had talks earlier in the conference about this kind of generalized ladder surgery for LDPC codes. I won't go into the details here, but the important idea is that by appending this ancillary system to the LDPC code block, we're able to perform measurements of arbitrary Pauli operators with still only the initial LDPC type measurements. Yeah, Dom?
Can I ask a question about that?
Yeah.
Do you use the older constructions in these papers or the more efficient new?
No, so we use the more efficient one. So sorry, I mean, I should, there's a lot more work that I will obviously cite in the paper, including yours and a whole bunch of other things. Yeah, I've kind of squeezed a couple of references in here that I guess are the first kinds of references in this direction. There's a whole lot of work here, but I didn't want to try and fit it onto the slide, but yeah, absolutely. So we're using constructions more like what's in your work, Dom. Yeah, absolutely, to make more efficient gadgets than this. And I think we've had even earlier at this conference examples of improvements on this bridging as well from Isha Swarup as well. So there's a whole lot of work on top of that. More precisely, I mean, the gadget system that we're using in particular is from this third reference here that we released last year from Iceberg. So in particular, the code blocks that we're using are a family of generalized bicycle codes that have these properties. So the idea is it's a family of generalized bicycle codes that we can instantiate across a range of different code distances. I've tabulated the 3 distances we're actually going to use in practice here in the table. But what's important about them then is that these codes allow us to have these different code distances. They can encode kind of 10 plus logical qubits per code block, which encoding multiple logical qubits per code block is what allows us a higher encoding rate. And if we look at the processing block, a full processing block now is going to consist of the n physical qubits of the code, plus another order n physical qubits that are ancillars for syndrome extraction when we do error correction, plus additional physical qubits required for this gadget system is going to give us this NPB, which is the total number of physical qubits actually needed for a processing block. And if we look at the ratio of the number of physical qubits for a processing block by k, the number of logical qubits per block, we can see that even up to distance 24, we need on the order of 100 physical qubits per logical qubit for this full construction that allows us to do arbitrary Pauli product measurements. And that's important because then it allows us to achieve these order of magnitude wins over a surface code that would need more like on the order of 1,000 physical qubits per logical qubit to really be able to do these kinds of operations using ladder surgery. So in particular then, we've picked these codes because they have really nice properties. So this is what we studied in this reference 3 down here. So in particular, these codes have the property that any arbitrary Pauli product, logical Pauli product on the k logical qubits of the code block can actually be measured using a set of 4 essentially static gadgets. So by that we mean you've got a whole lot of operations that need to be done internally in the gadgets to do the syndrome extraction circuit. But simply by rearranging or shifting around the position we connect the gadget to the code block, we can measure different Pauli operators. By bridging these 4 gadgets together and connecting them in different places, we can actually then measure any logical Pauli product of this code block. So that's what's shown in this animation here is a random sequence of Pauli product measurements, and an example of how that would be measured with that gadget system. In general, then, a processing block consists of basically the code block, the 4 gadgets that you can see, and actually 4 bridges, because we include a 4th bridge to allow us to connect to the neighboring processing block. And then if we compare to the surface code, we can see in the graph that we have this order of magnitude overhead reduction compared to the surface code as we go to more and more logical qubits. So the processing blocks really are the core modules of the architecture. So we wanted to benchmark their performance with simulations. So we did simulations using circuit level noise. We used standard depolarizing noise for this purpose. We also used most likely error decoding. So I should say a little bit about that. So the purpose of this work is not necessarily to demonstrate the classical control software that you would need to implement this. Clearly there's a problem in the field generally to solve how we can do real-time decoding to actually have a classical system capable of performing the kinds of operations necessary to run this quantum computer. We will have work out in the relatively near future from Iceberg about this decoding problem, but for our purposes, we were interested instead in just understanding the performance of the quantum architecture, assuming that we have the necessary classical software. So we used most likely error decoding, primarily because unlike something like belief propagation, there's much less risk that you run into something like an error flaw, simply because we know the most likely error decoding should be able to correct for up to d on 2 errors. So we're more confident than extrapolating our results to these very low logical error regimes where we're not currently able to do direct measurements because the failure modes are too uncommon. Yeah, Mike?
You say most likely error decoding, but what are you doing in particular? It's like some brute force approach?
Yeah, it's using like an integer linear programming thing. So yeah, it's a way to make it more efficient than completely intractable, but yeah, it is. Obviously, these are big calculations that we're doing to get these results. Yeah, Timur?
So there's no markers for the black line, so how do you?
Yeah, exactly. So thanks for bringing that up. So yeah, we're fitting an ansatz to this. So the idea is that we're fitting a single ansatz across the different codes. So I should say quickly, we've done both memory experiments and logical measurement experiments. So the memory experiments are where we're just doing an idle operation, but we also simulate logical measurements, the dashed lines. So we fit a single subthreshold ansatz that's constant, has the same parameters A, B, and C regardless of P and D. So although when the graph it appears as 5 different lines, solid lines and 5 different dashed lines, they're all based on the same ansatz fit that are based on the data that we've collected across the different codes. So we're assuming that with those fixed parameters, so we're extrapolating up in distance. Sometimes I think in other papers you'll see they put kind of distance on the x-axis and they'll show lines for different physical error rates and they extrapolate in the same way. It's one of these problems where you need a kind of 3-dimensional extrapolation.
So do I understand correctly that you have not simulated D24?
Yeah, we haven't done simulations for d equals 24. So we're relying on the fact that we have this code family structure. So we have the same method for constructing the circuits and the circuits for both the memory experiments and the logical measurements across all these different code distances. And we're able to construct that for d equals 24. The problem is really that you've got these very low logical error rates. So we don't have the means at the moment to get the samples that we need to do that. But that's another problem that we're also looking at Iceberg. I think like IBM said when they presented their work, probing better this low logical error rate regime, I think is an important problem for the field. Sorry, Mike, did you have something as well?
Yeah, sorry, a follow-up is that how close does like DPOSD get to these exact numbers?
So it performs well at the higher logical error rates. When we really push it down, though, that's when we're starting to get error flaws. So that's where we think there's still work to optimize better decoders there as well. And we'd be reluctant kind of to improve the decoder well enough that we don't see the error flaw in what we've probed, but to then extrapolate it beyond knowing that we had these problems. So as I said, we've got decoding work that we're doing, and then we've also, in parallel with that, got new methods we're working on to probe the low logical error rate regime. And we really want to present those two things together, I think, to be able to say, here's the decoder, and here's the justification that we're not going to run into error flaws we haven't seen yet. All right, so to summarize what we get from that, I mean, the main takeaway is that this justifies that we can get these low logical error rates that are relevant to this kind of large-scale quantum computing. So in particular, when we look at an application like RSA, per logical qubit per logical cycle, we need something in the order of 10 to the minus 14 error rates. So you can see that a distance 24 at 10 to the minus 3 and a distance 16 at 10 to the minus 4 should be sufficient for that. So those are the codes that we use when we get to that point. So that's the processing units and their performance. The magic engines then I'll introduce next. So far we've talked about how we do Pauli product measurements. As we talked about, we need a supply of T states as well to be able to actually do universal quantum gates here. So we've introduced this new concept of a magic engine. Typically people talk about magic state factories, which are ways to have some facilities that do something like magic state distillation and prepare magic states online that can then be put into some kind of cache and then injected into a code. We wanted to avoid this separation between the distillation and injection part of the process because of this reason that LDPC code blocks have many logical qubits in them. So you really want to avoid ever using a single a whole LDPC code block for a single logical qubit to host a T state and not have it do anything else. And you also want to avoid what I think work from IBM's done in the past, where you need to use surface codes, like large surface codes, to store these states as well. So the purpose of the engine is to allow us to simultaneously be distilling a new state in one logical cycle, while also consuming the state that was produced in the previous logical cycle through the processing unit. So that looks a bit like this. We've got kind of in pink is a processing unit. In green, we've got an LDPC code block. And then in this light green, or I guess it appears white on this screen, we've got an ancillary system. And the purpose is basically that we have on this LDPC code block, we think of partitioning the logical qubits into two sides that we call logical sectors, so two halves of the logical qubits. With one of these sides, what we'll call the left sector, we do a magic state distillation circuit, in this case a 15-to-1 distillation circuit, using noisy T states that we inject from an ancillary system. So this ancillary system is using surface or color codes, but much smaller ones that you need to actually store the high fidelity magic states. And we're doing things basically for a low enough logical error rate that we're happy with the input rate. We can just do something like a post-selected state injection circuit to prepare those noisy states. If we need to bring the error rate down, we can do something like a round of magic state cultivation just to bring that error rate down a little bit before we inject it. We're injecting that into that sector of the LDPC code block and doing that distillation. And then in parallel, we're also able to perform joint measurements with the other logical sector that's now hosting a T state from the previous logical cycle and the processing unit. And the idea then is that from logical cycle to logical cycle, we can just swap which logical sector we're using. In each case, one logical sector should have the T state that was produced in the last logical cycle, and the other one will be distilling a new one. Yeah?
Did I hear correctly you're saying you are using surface code?
Yes, so we're using surface code and color codes in this ancillary system, but we're using low distance ones. So when you inject the actual high fidelity state, you would need, for example, for using like D equals 24 LDPC codes, you'd need something like a D equals, maybe not quite 24, because there's some caveats in that, but you need a high distance surface code to actually store a high fidelity magic state. We're only using them for low fidelity magic states. So we're looking at magic states at like 10 to the minus 4 error rates that we're using to inject. So it's good enough if we have 10 to the minus 4 error rates, we can have something like a D equals 5 color code. If we have like a 10 to the minus 3 error rate, we do some round of cultivation and we end up with like a distance 9 surface code that we're injecting from. So there is some overhead, and that's what the ancillary system is. We would like to bring that overhead down and have something better than that. But the important thing is we're not using these higher distance surface codes.
So
The factory is in the LDPC code. Right, the factory is really the distillation circuit. It's the injected states we're talking about fidelities that are not so different from the physical error rate. There might just be some pre-processing if we want to make sure that we only need to do one round of distillation. And that's where we might use something like a very low level of cultivation.
And that's the main distinction between what you're saying factories are or these engines?
Yeah, the factory, generally when people talk about factories, they kind of omit this injecting stage, or they don't deal with it in much detail. They talk about you have a factory, make sure you've got enough qubits over here to produce the states, and then assume that it's put into some cache and you inject it. And with surface codes, that's just, there's going to be some surface code that's not going to be used for distillation while you're injecting, and that's kind of negligible. But it's more of an issue when you're talking about LDPC code blocks that, relative to the overhead of the whole scheme, are a lot larger. Yeah. So we're only using one round. So that's why I was saying that we have the pre-processing stage. So if we require a lower fidelity of the output than we can achieve with just one round of distillation, that's when we do something like some level of magic state cultivation within a much smaller surface code to inject it. So I think in Gidney's work, he does a cultivation round and then one round of 8T to CCZ distillation. We're doing a sort of lower level of cultivation and using really fault transversal cultivation instead, which in this regime can do a bit better, to get more to like 10 to the minus 4 error rates, but then doing this larger scale, 15-to-1 distillation that has this cubic suppression.
Sorry, what distillation you're using?
We're using 15-to-1 distillation. So this 5 logical qubits is based on this way the Litinsky does the magic state distillation, where with 5 logical qubits and 15 state injections. Yeah, exactly. You can break these into Pauli product measurements, and that then fits with the kind of setup we have here.
Does the bulk of the overhead here for these engines come from distillation or the cultivation?
It depends on the physical error rate. So for the 10 to minus 4 error rate, the ancillary system, you don't need cultivation. You really can just inject it at that error rate. For the 10 to minus 3, at the moment, I think the overhead from the ancillary system is larger than the distillation circuit. but we don't think that's general. I mean, part of the reason that we want to have these magic engines as modules, we think there's a lot of scope to optimize that cultivation part and the topological part. Ideally, we'd like to avoid using surface and color codes at all. But yeah, at the moment, the overhead is larger than we'd like it to be. But the key idea is we wanted to avoid a proliferation of these high distance surface codes that we're really going to blow up the overhead. So we've at least got to a point where the overhead's not dominated by the magic state facilities, which is really the important thing for the overall overhead. Yeah, Tom?
The parallelism here. So is it like one patch of surface code and then that you're putting one like sort of cultivated t-state in at a time?
No, so we have 15 surface. I mean, it's not necessarily 15. You can scale how parallel it is. At the moment, we're assuming you have 15 so that you don't have to worry about the problem of like getting new states. Yeah, we're doing parallel injections then. So the idea, like the key idea is that you only need Z-type measurements to do the injection, which makes the parallelism more tractable to do.
I was going to ask about that too with the measurement into the other block. Is that just because it's all on the same basis?
Yeah, I mean, yeah, that's right. So this is then the Z-type makes it easier as well. The hardest part of this process is the X-type post-selection measurements that you've got to do in the distillation circuit still need to be done in parallel with the Z-type measurement. So that is, I mean, there's a trick as well that we're using auto-corrected injection that means that those X-type measurements don't become like Y-type measurements. You don't have to push the Cliffords through. But you need to pick a particular basis where you don't have overlapping qubits. Basically, the framework we've got, you can do measurements that commute, as long as they commute qubit-wise, you can do these measurements in parallel. So you're able to just find a basis because this is larger. Yeah, you need, for each code, you need to design the parallel measurement systems. There's an assumption here about what measurements you can do in parallel that works for our particular codes. And then if you're using a different code, you might change the scheme, do less things in parallel and so on if that was a problem. But yeah, exactly. At the moment, we're using properties of the codes to find the right parallel basis. Yeah?
So for parts of the circuit, you're going to be doing arithmetic. Why not directly produce CCZs?
Yeah, that's a great question. So definitely, that would be an alternative so we could produce CCZ states. And I think that it's possible that is a good route to go. I think we want to explore that. The CCZs are going to introduce some complexity here. I mean, one complexity is just for RSA, you're doing Toffolies, it's good to produce the CCZs. For other things I'll show, like Fermi-Hubbard model, you're also requiring T-states. So we want to start from the T-state point of view, kind of for simplicity and for generality. In terms of the CCZs, I mean, then it's just you need to redo this circuit analysis of how you're doing the consumption of the CCZ states. Gidney has a way, I think, with surface codes to do the auto-corrected CCZ injection in one logical cycle. We would be assuming, I think, you need 3 logical cycles to do that, compared with the sort of, I mean, it ends up being 5 logical cycles to consume the T-state, do a Toffoli with T-states, because we need another logical measurement. But the wins are not as big as you'd expect until we get to the point that we can optimize this better. But it's a good question. I want to do that optimization, and I think probably in future we'll have CCZ states, because I think that's probably a better solution in the long term once we solve those issues. All right, lots of questions. Any other questions before I go on? All right, this is just a comment to make as well. I mean, we're using things like distillation and cultivation here, so there's some post-selection. So we just assume that if you fail to produce an acceptable state, you just leave it idle for a logical cycle. For the way we've set it up, that's never more than about 6%, so you just factor that into the runtime that you've got to scale up to account for these idle cycles. All right, so as I mentioned, I want to show a quick example of applying this to kind of a simpler problem than RSA. So in particular, there is more to the architecture than I've shown so far, but the processing units and magic engines are sufficient to do universal gate sets. So in problems where when I'm about to introduce isn't so important, we can jump in right now and look at how this works. So we can look at an example of calculating the ground state energy of the Fermi-Hubbard model for 2D L by L lattices. So I won't go into the physics of this, but basically a Fermi-Hubbard model is a model to represent interacting systems of fermions. It's hoped that systems like high-temperature superconductors you might be able to learn about by probing this. So it's a good kind of, not quite toy problem, a good practical but simpler problem to look at. And following this work by Al Campbell, where you can use plaquette trotterization to do this ground state energy calculation, you can make it so that you need essentially 2 logical qubits per site, so 2L squared logical qubits plus 2 ancillary qubits. And then the number of logical cycles is about 8 times 10 to the 6. It's kind of a quirk of this particular problem that the number of logical cycles is approximately independent of the lattice size. This is because you're working with a relative error. So this is the error in the energy estimation compared to the total energy, which is extensive in the lattice size. which means that as you scale up the lattice, the accuracy you need per site goes down, and you get some cancelling out effect. If you're interested in this paper, and I think also in this other one I'll reference in a moment, there's more discussion of when you need to do one or the other, but we've picked this as an example problem to consider. So basically, how do we compile this in the Pinnacle architecture? Well, in this case, we'll just take one processing unit. We'll make sure we have enough processing blocks to cover the logical qubits that we need. So if we have k logical qubits per processing block, if we take the ceiling of n over k processing blocks, that will give us at least n logical qubits. We pick a code distance that, based on the simulation results we had, gives us a good enough performance for this problem. We find that d equals 24 is necessary for p equals 10 to the minus 3. But for this problem, d equals 10 is sufficient for p equals 10 to the minus 4. We assign a magic engine to each processing unit as well to make sure that we have a t-state per logical cycle. And we get the physical qubit counts given by this. So what this looks like is basically the first term is the processing unit, and the second term is the magic engine. So these coefficients are kind of the number of physical qubits per processing block that are different because we have different code distances. And then that's multiplied to the number of processing blocks, which is what's multiplied to that coefficient. And then we're adding on the end the constant, which is the size of the magic engine. So if we actually look at what we get from that, if we put this into a graph, these solid points are what we get from the Pinnacle architecture, and we're comparing here to a surface code analysis that was also from Google by Kivlichan et al. And we've got in solid points, we've got the number of physical qubits required with the Pinnacle architecture, and we find that in the sort of interesting regime for near-term applications, which I think is realistic, probably 16 by 16 lattice or that sort of order, to go beyond what's classically tractable, we're looking at the range of tens of thousands of physical qubits compared to hundreds of thousands of physical qubits in that regime with the surface code analysis. I should comment briefly on the runtime. For this application, unlike RSA, we didn't do a lot of work on improving the runtime. We've really just optimized this for the overhead. But I just wanted to emphasize, these aren't crazy runtimes. You have to run multiple shots on this to actually get the ground state, which is a problem we've not worried about in this. But you'll get talking in the order of minute runtimes per shot for the fast code cycles, and then for slower code cycles, going up to days. And there's room for optimizing that. Yeah, Dom?
Well, I think I missed something with the, you have like many blocks of the
Yeah.
memory while wave processing is happening. Are you doing the parity-based computation across everything, or are you only compiling out the Cliffords in the blocks?
Yes, I'll talk more about that in a moment, but yes. So at the moment we're doing, it's only in this context with one processing unit, we're doing the parity-based computation across the full processing unit of all of the blocks. So we're only doing one logical measurement per processing unit per logical cycle. But we'll talk in a moment about what you can do to change that when you want to actually parallelize more meaningfully. But as I said, I mean, when we're optimizing for the space rather than the time, that's not an issue. I'll talk right now about what we're going to do to allow ourselves some scope of parallelism. So this is what Dom's question was kind of hinting at, which is when you use this parity-based compilation, one of the reasons that people don't like to use it in lots of contexts, like surface codes, and prefer alternatives like active volume compilations, is there is some challenge in introducing parallel operations in this framework. So in particular, what happens if you remember back to the parity-based computation steps that we took, we were commuting all the Clifford gates through all these measurements. So if we think about all the Clifford gates that occur beyond a given, before a logical measurement, we call that the Clifford frame. All of the Cliffords have to be pushed through that measurement. If the Clifford frame includes lots of C-knots that entangle that logical qubit and eventually spread out, entangling to many logical qubits, as you push that through, the Pauli product measurement you need to do to inject a T-state on one logical qubit becomes a very high weight logical Pauli measurement across many logical qubits. And that part itself isn't a problem in that it's in our framework, it's just as easy to do a high weight logical Pauli measurement as a single qubit one, but it does create a problem when we want to do gate measurements in parallel. So you would think in a normal Clifford plus T circuit, if you have two T gates, as long as you have the T states required to do these, you should be able to do these in parallel. But in the Clifford-based compilation, they're likely to end up being overlapping measurements across the multiple logical qubits. In some contexts, you can do these measurements in parallel, as we were talking to Dom about before, but in general, these are going to be logical measurements that will have like X and Z and Y type measurements all mixed together on the same logical qubit. It's very difficult to do them in parallel. It requires a lot more work. So we avoid that and assume that we can't do those in parallel. So what that means is we need some way to control what's going to happen to this spreading out of the measurements. So there is previous work, so I don't think I put it on the slide, but there is previous work from a paper called Extractors. Sorry, I thought I'd turn that off. Let me just, that's come out every hour. I thought I'd stop that, but I guess not. So there's a paper called Extractors that looked at some of these these systems of gadgets and how we can do the surgery that had one proposal to solve this problem, which is that essentially you can do CNOTs as actual Pauli product measurements when they act between different blocks, and that prevents you having to push these CNOTs through. We've got a different solution, so we think that solution in some contexts works well, but it does have the cost that if you have a circuit where some parts of the circuit have a lot of these interblock CNOT gates and other parts don't, then you have to make a choice. Do you pay for the cost of all of those CNOT gates, or do you accept that you can't do parallelism in the other part of the circuit? So instead what we want to do is we want to have something more flexible, and we achieve that through what we call Clifford frame cleaning. So essentially the idea is that where we have these CNOTs that have acted across them in entangled different blocks, we can choose at any later time in the circuit to clean the Clifford frame off a processing unit to separate two processing units out again, using a number of measurements that's constant in the number of CNOTs and only depends on the number of logical qubits. So if we look at that stage by stage, before we've pushed any CNOTs through, we can have two different processing units that act in parallel. But if we reach a point where a CNOT is pushed through these from that point on, we now treat these two processing units as a single processing unit. And from that point on, we assume that we can only do one logical measurement per logical cycle on that entire joined unit. But then at any later time, we can choose to perform a maximum of 4K cleaning measurements, where K is the number of logical qubits per processing unit. And by doing that, we're able to clean this off and separate the frames out again, so that now we can do it in parallel again. So to be clear, the way that these modules are defined, we're never going to do more than one logical measurement per logical cycle on a processing unit, but we can choose how big or small the processing units are. So at one limit, the processing unit could be one processing block, and we could choose how much to join or separate them. In general, for this RSA problem, we're going to have kind of a few processing blocks per processing unit, and then we can choose, as I say, to track through when different processing units are joined or separated to keep track of when we're able to do gates in parallel or not. Yeah, Mike?
These measurements, they have some logical effect on the circuit, but then you can like cancel it later or something, these cleaning measurements.
Yeah, they're equivalent to doing the actual Clifford gates, right? So if you think about, you've commuted these Clifford gates through, right? So you can think about your circuit now before you, like when you look at this line of logical measurements, you have a choice that you could perform all of the Clifford gates that have been pushed through at this stage, right? And then you wouldn't have to push them any further through. This is saying that you don't actually need to do all of them, right? You can decompose that arbitrary Clifford operator into a set of up to 4K. What they end up being is pi on 4 rotations that you can do them with one ancilla in a sequence of 4K logical measurements. So it's like you're kind of, in a sense, undoing what the Cliffords were instead of pushing them through. That's the sense in which it's cleaning, right? It's like cleaning off all this stuff that you don't want to keep pushing through. Yeah, Dom?
So the difference to extractors is you're like dynamically going to change this. Because I think in extractors we allow the possibility to do, combine a bunch of stuff into one.
Yeah, exactly. We basically have it as a freedom of the compilation to decide when to perform cleaning. It's not something we use in a lot of detail. I'll talk in the next slide about this. There's one particular place we need it now, but in the future in general circuits, the idea is you could have a compiler that has some sort of resource cost associated with doing this cleaning and optimize over the space-time cost to just find the right time to do this. Exactly. So it's exactly, that's the idea, that it may prove to not be worth doing this cleaning before some measurements, but it is before others, just based on how many operations you need to do. All right, so there's one more module of the Pinnacle architecture I want to introduce now that I've saved till now because it's optional and because it depends a little bit on this Clifford frame cleaning, and that's this memory. So memory in this context is basically just used when we have a large number of logical qubits that we need to store coherently and perform error correction on, but we don't need to be doing a high density of logical operations on them. So in our context, it's simple enough to think of these as just like LDPC code blocks where we don't equip them with a full gadget system to be able to do arbitrary logical measurements. So essentially, they're just code blocks, and you save on that overhead. What this is analogous to, I mean, kind of peeking ahead to what we're talking about RSA, in RSA, Gidney uses this concept of cold storage and uses yoked surface codes that don't allow the same density of logical operations. We've got something along those lines, but now in our LDPC code architecture that's obviously with a view to being able to use it for that application. So the idea then, how do we use this memory? Well, you have ports. So the idea is a port is what allows a processing unit to access a window of W logical qubits of the memory at a time. And this basically amounts to just one gadget and one bridge that's tailored specifically to allow us to do the kinds of measurements that we need to access that window of memory. For the kinds of operations that we need, these like lookup operations that you need for RSA, it suffices to just be able to do measurements that act as Z-type measurements on that window of qubits. and then you're able to bridge that across or adapt that across to the processing unit to do arbitrary logical measurements in the processing unit. So the idea then is that what you get is you've got the potential, I'll bring up this, to have multiple processing units sharing a memory. Because we're able to have multiple ports accessing different windows of memory, all of these measurements that we're doing act as Z-type on the memory, so they all commute with each other when you have different processing units accessing via the port. And by using Clifford frame cleaning, we're able to clean the ports after we finish an access, which means we can then reconfigure the memory, which we do just by doing kind of nearest neighbor rearrangements that allow us to cycle around the blocks, the windows of the memory, so that we can allow all of the processing units over time to access all of the memory without them becoming entangled to each other because the measurements commute and because we've cleaned these ports off so they're not kind of pushing any Clifford frames back from the port onto the other things. So where does this leave us in terms of RSA? If we get now to the crux of the talk and the key result, the way that we're doing the compilation for RSA, we're following closely this work that I've mentioned a couple of times by Gidney that he presented last year. And in particular, this is focused on how you do modular exponentiation, which is the dominant part of the algorithm that you need to do. And essentially, the way that it's laid out then, for factoring an r-bit integer, you need 2 registers of logical qubits. You need a working register. So the working register is going to need to do a high density of logical operations. This is in Gidney's work what he calls hot storage that's able to do these ladder surgery operations in fast time. So we're going to realize this working register by a processing unit with capital K, where K is the number of logical qubits in the working register, over lowercase k, the logical qubits per processing block. Enough processing blocks in the processing unit that we're able to realize all logical qubits. Importantly, the working register, using this prime number residue system arithmetic idea that was implemented by Chevignon et al. In that reference, only requires you to need order log of r logical qubits in the working register. So for example, in this, an example might be you might need something on the order of 150 logical qubits in this working register, which makes it obviously a much smaller system than you might expect for a 2048-bit RSA decoding or decrypting. But you also need this input register that does have a number of logical qubits that's linear in the bit size of the number you're factoring. So in particular, it's of order kind of half the number of bits plus some extra parameter that depends on the code parameter of this Ecker or Horstad technique that's referenced there. So essentially then the input register can be implemented in memory because we're only going to need to use it for these lookup operations. So if we break that down, what we get is the working register then has this number of physical qubits here that depends on the number of logical qubits in the working register, which is relatively small, and the number of physical qubits in the processing block, and then obviously has this magic engine. In the memory then, we're going to need a larger number of logical qubits, but we're going to have some savings from the fact that they're only code blocks, not processing blocks, and then this NG plus NB is this extra bridge and gadget for the port. So when we actually put that into practice, then what we can find is for the example of 10 to the minus 3 error rate, so the same physical error rate that Gidney considers in his work, we require a minimum of a little under 100,000 physical qubits to be able to compile this. You can see then what this looks like is actually, it's dominated by the memory. So at 75,000 of the 100,000 odd physical qubits are in the memory, which is coming from the fact the memory just has so many more logical qubits. But we're able to still fit it into that 100,000 physical qubits. If you go to a lower logical error rate, like 10 to the minus 4, as I've said, you can use a lower distance code, a D equals 16 code, so you can almost save almost half the resources there and get close to 50,000 physical qubits in that physical error rate regime. But this basic compilation is really the crux of how we get that headline result. But I don't want to finish there because it would be dishonest to present the physical qubits without commenting on the runtime. It would be meaningless to give a number of physical qubits if this factoring is going to take years or decades to do. So I want to get into how you can actually do this feasibly on different hardware platforms of different parameters. So in particular, when you apply Gidney's algorithm and compile it to our architecture, you find you need something on the order of 10 to the 12 code cycles to do that. If you have microsecond code cycle times, that ends up coming out to weeks. But if you have millisecond code cycle times, then it becomes completely infeasible, and we're getting into decades of time. So we need to do something about that using parallelism. Fortunately, Gidney's algorithm has some scope to be parallelized. For his study, where he's really looking at this fast hardware, like superconducting qubits and focusing on bringing down the space overhead, this isn't a trick that he needs to use. But when we're looking at these slower hardware platforms, it's going to be important. And the idea is basically the crux of the algorithm is this loop over this very large number of prime numbers in this prime number residue system that are then kind of coherently added together in an accumulator as we go. So that means that we're able to rearrange this so that instead, as we go through, we can have multiple different working registers working in parallel with subsets of these primes that each have their own accumulator, and then do some kind of parallel reduction process at the end to combine these accumulators together before we perform the measurements. Yeah, Andrew?
I just wanted to ask about your term code cycle.
Yeah.
I had the impression like the 1 microsecond case is kind of like for a single physical level operation, but actually that's not, is that not?
So this, sorry, so this is,
for 1 microsecond code cycle, I'm running some, what do I have to do in the 1 microsecond?
so the microsecond is a round of syndrome extraction. So it's not the physical operations, right?
So that is potentially like multiple, order, some handful of C-naughts and
yeah, I mean, so we're looking at weight 6 checks in this code. I didn't mention that, right? So we're looking at, that's right, on the order of 6 rounds of gates and the measurement, and then obviously the crux of this is also potentially some transport time, which is going to be associated with using LDPC codes. So this microsecond code cycle time is what's assumed by Gidney for the surface code. Obviously, he's looking at applying it to the surface code, so it's going to be a hardware-dependent question of how the code cycle time is going to be different for different codes. But that's why we've considered a range of code cycle times as well, is that this thing potentially could be larger for different codes. It's going to depend a lot on the details of the hardware. I mean, I guess hardware platforms where the time's dominated by memory, it's not going to make, by measurement, it's not going to matter so much using LDPC versus surface codes. Ones that are dominated by transport, obviously, where you have more challenges implementing these LDPC codes. But yeah, this code cycle time is, that's right, it's comparing to that same terminology it's using Gidney just for LDPC codes instead. Yeah, Timo?
I would expect it would be like logical cycles.
I've multiplied by the kind of D to get this number. So for simplicity, I've kind of, the 10 to the 12, I think in Gidneys, it's something like 7 times 10 to the 9 Toffelees. You multiply that by a few, and you get sort of on the order of 10 to the 10, or a few times 10 to the 10 T-gates, and then you multiply by this, and you get the number of code cycles. So yeah, I've crushed a lot of stuff in there to try and make it clearer. Maybe I made it less clear. Sorry, Dom?
This code cycle, is that have to be the same for the where the logic's happening and where the storage is happening? Because the things you're measuring will be different, right? So it seems like it would be a little bit worse where the logic's happening.
Yeah, we're assuming, yeah, that's right, we're assuming it's the same. I mean, there is a good question about whether you could optimize this so that you could allow a longer
What weight do you get up to on the logic?
So say that again?
What weight do you get up to on the logical gadgets?
So the weight will be, I guess, as the checks themselves are 6. We're going to have some increase in the weight from the fact that we need to bridge these things together in the gadgets. So I think, I would have to check the numbers. I think it's going to be in the order of about 8 or 9 once we account for the full thing. There is, as kind of using the sort of techniques you've done, there's obviously ways to try and reduce that as well, to some extent using some small additional overhead. But yeah, this isn't blowing up like crazy. When we do the parallel operations again, that's again where we need to do some kind of weight reduction too if you're attaching multiple gadgets in one place. But yeah, 100%. So definitely what the code cycle time is something that we're largely agnostic to in this work. I mean, we considered trying to develop a model of that, but realistically, this is kind of a hardware agnostic architecture. What we want to do instead is really look at a range of code cycle times across 3 orders of magnitude and see what you'd need in different parameters. How that's going to come out then in different hardware platforms is going to be partly about the hardware platform, partly about how you do the right code design here anyway. So we didn't think it was worth sort of doing a detailed model that would really be a toy model of what this would look like in terms of code cycle time. We thought instead, let's make the code cycle time a free parameter, and let's see how this changes across different code cycle times. So if we put this into practice then, just to finish this story, right, the idea is if we now allow ourselves row processing units, we'll assume row is some natural number that divides the number of primes that you need to parallelize. The idea is that you can duplicate these processing units, but allow up to an order of hundreds of them to share the same memory by having this trick of the parallel ports, which means you can reduce the runtime by this factor of row up to this additional log row factor that you need to combine the accumulators at the end of the process. But you do this without having a direct space-time trade-off. So in particular, what's shown here is that the increase in the logical qubit, sorry, I've warned this is difficult to do. The increase in the logical qubits that you need is gentler than the decrease in the runtime, coming from the fact that the architecture is dominated, the overhead is dominated by the memory in the low parallelism regime. So the fact that you don't need to duplicate the memory, only the processing unit, means that you do get a genuine space-time win in those first kind of order 10 rounds of parallelism in particular. And that kind of nets out to being something like an order of magnitude win in the space-time, which is nice when you get to these very parallelized schemes, that it performs slightly better than you would if you just had a naive direct space-time trade-off. And this is, again, what this looks like. I can now sort of say what this picture I keep showing is. So this is an example of what it would look like in your architecture if you were going to factor with trapped ions in the order of 3 months using 1 million physical qubits. So you'd have something in the order of 80 processing units around this memory with magic engines assigned to each of them. You have a lot more physical qubits than you do in the previous slide because you're doing this parallelism. But the idea is if you want to bring the runtime down further from 3 months to 1 month or a week or so on, you would keep scaling up these number of processing units, and you have that trade-off there, which is what I want to talk about on this last results slide. So this is, as I said, we wanted to consider the whole spectrum of parameters of code cycle times and also look at different physical error rates. And we also then look at what would happen if you allow a different range of number of physical qubits. So what these heat maps show is essentially, given this code cycle time and this number of physical qubits, what would the optimal runtime be on this architecture? And that's shown for 10 to the minus 3 error rate and 10 to the minus 4 error rate. And on the bottom, we've got, if you have particular error rates and code cycle times and you target a particular runtime, what's the minimum number of physical qubits required to do that? I don't know if I said earlier, KQ is just kilocubits, so like thousands of qubits, and MQ is megaqubits, or millions of qubits. So importantly, then, we can see that we're getting just a touch below this 100,000 physical qubits here, which is the basis for our headline result, saying with this 10 to minus 3 error rate, you can achieve this 100,000 physical qubits. If you look at where that line's intersecting, it comes out, as I said, to about a month at 100,000 physical qubits. But you can see that you don't need to go very far up, only to about 150,000 before you get to a week. So you can really bring that runtime down using these nice parallelism trade-offs that I talked about. If we look at different hardware platforms, so if we go to something like I mentioned, like trapped ions, where we might expect to have a better physical error rate, more like 10 to the minus 4, but we might expect a code cycle time more on the order of a millisecond, then we're looking at a higher number of physical qubits simply to account for the fact that we're going to need a lot of parallelism to finish this thing in a feasible time. So for example, if we want to do this in a month on this trapped ion computer under those assumptions, then we're going to need more like 3 million physical qubits. But I should emphasize this is an improvement on what we had before. So certainly if you take Gidney's work, obviously he's focused on the superconducting, so he doesn't try and optimize it. But if you naively applied that to the trapped ion case, it would just be intractable to run it because it's going to take 1,000 times as long and it's going to take 1,000 weeks instead of 1 week. So it's important to have this trade-off to show that there is a route to do this on slower hardware platforms. And I'll talk in the next slide about how we might improve on that further. If you looked at neutral atoms, so if we look at the case where you might expect a physical error rate more like the 10 to minus 3, but a code cycle time more like a millisecond, then again, we're looking at more qubits still, so we might be looking at 13 million qubits there. But again, the idea is that we do have a path to do these for different hardware platforms, and then it's a question I'll talk about now, I guess, about how we can go beyond this and get better results, including for those hardware platforms. So this is my last slide, so I want to give kind of a summary and also an outlook of where we're at with it. So I want to emphasize that surface code architectures have had years to be optimized and may only have limited room for improvement in terms of these benchmarks. That's not just me saying it. I guess the authority on these kinds of things is Gidney, and he says in the conclusion to his million qubit paper that without changing the physical assumptions, he sees no way to reduce the qubit count by another order of magnitude. So to be clear, we have changed the physical assumptions by allowing LDPC codes instead of surface codes. We're dropping the physical assumption of nearest neighbor interactions while keeping the other physical assumptions. So our work in no way contradicts this, but it does suggest that there is reason to think that these gains may have been pushed towards their limit. 1 million physical qubits may not be so far above what you really do need on a surface code architecture to do this kind of factoring. Whereas LDPC code architectures are really just getting started. This is one of the first of these kinds of architectures that have been presented. We can think of a lot of ways already we can improve on this, and Chris already suggested using CCZ states, but that's just one of many, many things we could try to do. What we're particularly excited about is the possibility of using higher rate codes to reduce the physical qubit count. So we're using these generalized bicycle codes, but there are higher rate LDPC codes. If we can find ways to make these codes plausible to build the right gadget systems to solve all the technical problems, there's no reason that we couldn't plug better codes into this and really bring that physical overhead down. And we're also very interested in fast surgery, which was published by some of my co-authors at Iceberg. last year, which is a way that we can reduce the runtime by taking these logical cycles and making them take on order of a constant number of code cycles instead of order D code cycles. So it's really the analog to what in topological codes is often called single-shot fault tolerance. Fast surgery is a way to achieve that with LDPC codes. We haven't implemented that into this architecture yet. It's an ongoing work to put that into practice for these kinds of higher distance codes. But when we're able to do that, we can look at getting another order of magnitude of reduction in the runtime. It would make some of these questions about the code cycle time kind of moot as well. It would give us a lot of space to scale them up. And what we're looking at then is the ability to bring that runtime down by an order of magnitude, or for fixed runtime to bring the physical overhead for these slower hardware platforms down an order of magnitude as well, which is where we might start seeing for something like trapped ions closer to these hundreds of thousands of physical qubits. So if I want to take one summary away, we've seen the Pinnacle Architecture allows factoring with 100,000 physical qubits while also supporting the parallelism required to achieve feasible runtimes on a full range of hardware platforms. But we think this isn't the end of the story. So expect to hear more from Iceberg, and don't count on 100,000 physical qubits being the true number of physical qubits needed to break RSA. I wouldn't bet on that.
Thanks very much, Paul. Wow, lots of questions. Okay, Chris.
Yeah, so it's nice to see that, kind of some of the improvements that we do with QLDPC codes are kind of panning out. And so one thing that I was wondering is, the folks at IBM, the hardware that's fast typically has fixed connectivity. Maybe you have long-range gates, but it's got to be fixed. So is your kind of install system and stuff like that, is that fixed? Because you want to measure a bunch of different ones.
Yeah, that's a great question. So it is, it's kind of, I'm going to have to go back to it far. It's kind of quasi-fixed. I mean, it depends, and this is something that I need to talk more to experts on the superconducting qubits to know how this would net out on the superconducting qubits. It's fixed in the sense that the vast majority of the operations here are happening within these, well, not black boxes, these colorful boxes that are labeled as the gadgets. Those circuits are fixed. What's not fixed is where it connects to the actual code block. So that may be a challenge for superconducting qubits. I'm not saying that people at IBM missed a trick by having this extra time overhead. I'm sure that it was based on the considerations of their hardware. But definitely that's an interesting thing to consider as to what extent we're able to adapt that to that. Certainly, there are potentially other hardware platforms. So I think spin qubits are very interested in the idea they might be able to get fast code cycle times while also having the ability to shuttle around. But yeah, part of the motivation as well, of course, of looking at these different error rates and code cycle times is that we know that LDPC codes are something of interest to different hardware platforms because they have particular challenges for superconducting qubits.
One could make the argument the reason Andy makes the physical assumptions that he does is because this kind of square lattice and nearest neighbor connectivity is the only thing that's been experimentally demonstrated with even close to the number of physical qubits that you would need to run these kind of algorithms. And so I wonder to kind of, obviously we don't have the physical hardware yet to run the LDPC codes that you're talking about. So I wonder, in order to reach this kind of 100,000 qubits that you talk about, what are we missing in terms of the physical hardware, and how close do you think we are? So if you could give me a view to...
Yeah, no, it's a great question. And I think going back to what we said with Chris as well, I think it varies a lot from hardware platform to hardware platform. Definitely, I think when you look at these more atom-based platforms around neutral atoms and trapped ions, I think this concept of shuttling around is quite well developed. I think there's obviously a lot of technical challenges in all of these hardware platforms to obviously get to the large-scale quantum computing. But I think there are certainly models around the shuttling and the plausibility of the transport that are the essentials of what we'd need in terms of the hardware. So I think the hardware question, I would defer to the hardware experts to a point. I think what we've heard from partners we've worked at in some of these platforms is that they're confident with that shuttling side of things. But I think Chris is right as well to obviously raise that different hardware platforms have different challenges. In terms of other things to consider, I'd raise as well, there are definitely classical control questions as well, so I'd like to get more into this decoding, and as I say, we'll have work out on the decoding as well. I think that's one of the challenges LDPC codes still have as well, is to make sure we can do this real-time decoding, but I think that's a challenge as well for surface code real-time decoding on these very fast hardware platforms too. But certainly, our outlook at Iceberg is that we're here to really look at this LDPC code potential and try and put it into an architecture. And now that we've got this design, we want to work with hardware companies to really see Firstly, do they think it can be implemented? And if they don't, then we'll go back and we'll design something else that they think can. But secondly, exactly to ask them the question you're asking me, is to really go to the experts and say, which parts of this do you think are a problem? Which parts do you think we might imagine as a problem in the theory world but actually work out? But 100%, this is all part of what I said. It's really the start of the story. What we want to avoid, I think, with what we're doing with Iceberg is the risk that the great work being done with LDPC codes by a lot of the people in this room never gets translated over to the hardware world. So what we want to do is to say, let's take the theory results, show what an architecture would look like, and then let's talk to the people who actually have the hardware and see under what circumstances they can implement it and what it's going to look like implementing it. This is in no way to criticize. I mean, as you said, the reason Gidney's chosen these parameters isn't because he dreamed up that it's nice to have nearest neighbor interactions. It's because he's talked to the hardware experts internally and obviously knows what they expect to be plausible. But we want to consider the possibility that there could be other regimes and make sure that we're ready to offer that architecture where those regimes are feasible.
Yeah, so thanks for the great talk. It's really exciting work. I'm particularly interested in the second to last slide.
Yeah.
Talking about how you can increase the number of qubits and reduce the runtime of the algorithm by doing some parallelism.
Yeah.
Is this algorithm dependent, or do you think you could do this for, like, is this specific to shores where you can do this, or will it depend on, you know, the underlying circuit of the algorithm?
Yeah, it's a great question. So in general, it definitely depends on the underlying circuit. So the concept in what it looks like generally is this idea of Clifford frame cleaning, right? So the purpose of this is to create a general framework for this kind of parallelism. The reason it works well for the particular algorithm here is because it has this nice structure that you need to do this for loop over a large number of prime numbers, which essentially means you naturally get this decomposition into a lot of operations that have very little interdependencies, and that means that you can naturally split them up in this way like this. What it would look like generally in a more general circuit is you might start with something like this, but you would have more intermediate interactions between these processing units. So you would think of, in this Clifford frame picture, some of these units are going to join together for periods of time, and you're going to have to incur the cost of the fact that now operations across those two units are done in serial, and then you're going to clean them apart. So in general, I think it's going to be a much more interesting compilation problem. In some ways we're lucky, in some ways we're unlucky maybe that it's simple in this case, but definitely for general circuits, it's going to be a non-trivial compilation problem to see what you can do with that.
Just one more question.
I don't know if you can say this, but kind of, if you're optimistic and say the noise strength reduces by a factor of 10, and you could do this fast surgery, what's your feeling on the physical qubit count?
Yeah, it's a good question. I mean, I guess if you think about the order of magnitude going down, I guess that calculation we've done, right? So definitely you can say that now we're over in this regime instead of the other one, or I guess in this row. So we've got that number that bring the physical error rate down by that order of magnitude from 10 to minus 3 is going to look at, you know, this order of close to a half reduction. So we're looking at 50,000 plus physical qubits. The fast surgery then is going to be more relevant to these slower hardware platforms. I mean, the fast surgery isn't going to allow us to bring this 100,000 qubit number down because that really is the bottom of this, right? Applying the fast surgery is going to increase or decrease the runtime by an order of magnitude.
Yeah, I guess I meant like for these slower platforms with fast surgery.
Yeah, so the fast surgery then for the slower platforms, I would, as a rule of thumb, say it's going to be about an order of magnitude, right? So we're looking at about on the order of 25 code cycles at the moment to do these, 24 code cycles? Sorry, it's 26 because it's in details, but 26 code cycles to do this. We're looking at one or a few, right? So call it an order of magnitude fewer code cycles. So bring this runtime down by an order of magnitude. What you can think of doing then, I guess, is what currently takes, I guess, a month, I guess is an order of magnitude is close to now. What can now be done in a year could be done in a month. So if you want to be optimistic, I mean, maybe this is a sort of number. I wouldn't put that as the end of the story as well. I think as well that there's still potential for the high rate codes as well. I wouldn't rule out that you can do it with 100,000 physical qubits on something like trapped ions as well. But that's why I'm saying to stay tuned. We'll find out.
I hate to cut off questions, but our lunch is sitting on the table cold. So let's thank Paul again for